defined previously what is a measure space, okay, and we did several examples of measure space, measurable space, and then defining a measure of them, and then we defined, and then we did the several examples of measure as well, and then we ended at how to integrate simple functions. Okay. With respect to a given measure, generalized measure mu. Okay. So in today's discussion, we would like to talk about question and its answer, that for what class of functions we can define what? Integral of f over x, okay, with respect to some measure. Okay. This is what that we would like to. We would like to typically talk about which functions can be defined or whose integral can be defined as with respect to the measure. So we'll talk about those functions, and we'll also talk about some examples of it, some of the key properties of it, algebra of it. We're not going to talk about how to define the integral of such functions in today's discussion, but essentially I'm going to talk about the class of functions for which you can have such notion of. Okay. So what I would like to essentially define, so the class of functions for which you can define integrals is the class of measurable functions. Class of measurable functions. But what do we mean by a measurable function? So imagine if I have a measure space, okay, then as a definition we say that a function f from x, on the underlying set actually on which you have this sigma-algebra A into R. So there are various ways in which you can define a function f from x to R. Is called A measurable. In other words, measurable with respect to the sigma-algebra A. Okay. If what? You take a set of the inverse images, so it's like take those x from x for which f of x is bigger than every a. So in other words, for any a, so no matter what a you choose, if you have this pre-images, because if you see, how can I write it actually? So this is nothing, this is f inverse of what?
A to infinity.
So a to positive infinity. Okay. There's nothing but f inverse of a to positive infinity. So in other words, if the inverse image of a to positive infinity, this roughly Borel's set, belongs to a, okay, for all a in a, for all a in R, okay, we call such functions f as a measurable. Are you getting the point? So essentially, you want to prove a function, or you want to see a function is A measurable or not. You have to just take that, take an arbitrary semi-infinite interval, okay, and see the collection of its preimages. And if the collection of those preimages is contained in sigma-algebra A, you call that as A measurable. Okay. Why we are defining things in such a way? I mean, if you remember what we did, that imagine you have a function f and you want to integrate it. Okay, maybe over some interval a to b. So one way is the Riemann way of doing it, that you split the interval and you partition it. Okay, and then you create the rectangles which approximates some chunk of the area under this curve, and then sum up all those rectangles and you get the area. Okay, but the Lebesgue way of doing it is a bit different. So what you have to do, you have to basically partition, okay, not the x-axis but y-axis are the domain actually. Okay, and you take, for example, an arbitrary subinterval jk, okay, and take a point from it, maybe some yk, or maybe the infimum of the set jk, okay, and then consider the inverse images of jk actually. So in order to find the inverse images of jk, so what will be the inverse images of jk? These would be the inverse images of jk. So this chunk on x-axis is going to be the f inverse of jk. Okay, and then you sum up yk and f inverse of jk's, you get what you call essentially the integral of f. So that's what the rough sketch is. Now, the key trouble here is that you want these guys to be in the sigma-algebra. Okay? No. Okay. I must put a mu here. So the mu of, so it's like a yk multiplied by the mu of these inverse images. Okay? And then take the sum actually. Now, obviously, if you want to operate mu onto these guys, then these guys must be in the sigma-algebra, because mu is a map from sigma-algebra into the R actually. Are you getting the point? So all such functions for which you roughly take an interval and take inverse images, and their inverse images are in the sigma-algebra A, you call such numbers, such sets as such a map as a measurable map. Okay, and if you have such a map, then such kind of an expression makes sense actually. So it's well defined essentially. So therefore, you have this definition like this roughly. I mean, if you see now, you can see the analogies that why you are defining a measurable function in this way. Okay, because you want these guys to make sense. Okay, are you getting the point? Good. So function is measurable if this is true. So let's do some examples, and then we'll do some of the equivalent formulation of these guys actually. So let's do some examples. So what are some of the examples of measurable maps? Okay, what are some examples of measurable maps or measurable functions? Okay. How about the function? So define, so you have this underlying space, for example, any abstract space, x, a, and mu, any abstract space, and you take, okay, maybe for the time being, maybe we can keep this mu here, but this is a bit unnecessary. at the moment here, because when we are defining this, we are not using mu. Okay, so I mean, if you wish, you can keep this mu, but if you wish, you can just take this mu away at the moment from it, that because you are not using any mu to define that. So purely you need a and x in order to define a measurable map. So take any x and a, and take a function from x into r, which is a constant actually. So it's constant for all x and a. For all x and r. Is it measurable? What we have to do, we have to take an arbitrary semi-infinite interval, okay, and consider its inverse image. So what we can say about the inverse image of this arbitrary semi-infinite interval? Would that be same?
Inverse image.
So you have to think that whether the C is inside this interval or not actually. So that's what makes it the key thing. So if C is not in this interval, then what should be the inverse image of these guys?
Infinity is
So if inverse is the empty set. Okay? If C does not belongs to a to infinity.
yes, sir.
Okay? And if it does belongs to a to infinity,
Then it's whole.
then it's whole x actually. Okay? Now what follows from here, that whether f inverse of a to infinity is empty, it's in a. If it is x, it's in x actually. So every constant function, you define a constant function on a measurable space, it must be constant. Okay? Here is another example, and think about that, why this should be. So take f of x to be the indicator function of a. And this a is obviously a subset of x for now. Alright? So if you apply f inverse onto an arbitrary semi-infinite interval, what outputs you can expect?
If
So 0 belongs to this,
So you have different things actually.
0 and 1.
So one of the possibility could be
this
Of one.
interval is in A, it's,
if this interval is in
I mean,
A,
If this interval contains 0 and a,
0 or 1,
One.
contains
okay. So one of the things could be that okay, if it is contains 0 and 1, okay, then what?
x,
It's equal to
whole x.
everything. How about if it doesn't contains both?
Empty. Empty.
It's empty. But there will be a third possibility as well actually.
One of
You can say that okay, 0 belongs to a to plus infinity
a contains.
and 1 does not, then
First one is a complement, second is
this would be a complement.
second is
And if 0 does not belongs to a to plus infinity, but 1 belongs to a to plus infinity, then what will be the consequence?
a.
Then it must be
A.
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 Okay, so this is what we're trying to do. The set of outputs.
Yes, sir.
Is this guy measurable?
Yes.
Yes, sir.
We
Yes.
are
All
happy with this.
sets are belongs to.
We are happy with this. Are we happy with this?
A,
A अगर belong करता है तो
Is A is in the calligraphic A. So is every subset of X is also A.
अच्छा
A
A is a subset.
So is sigma algebra always a power set of X which contains all subsets?
no.
So it could be a subset of A. Then what we should say?
if A belongs to calligraphic
Okay. So you're gonna say
is
that then F is measurable if and only if A is in calligraphic, and that's it. You have to assume this. So what does this shows? That if you take a measurable set, then its indicator function is also measurable. And if you take an indicator function which is measurable, then that guy must be an effect. Maybe this would be a good exercise, because if you see, I've just proved this. That if A is here, then this guy is measurable. And you have to prove this side as well. So think about verifying it. That, okay, if this guy is measurable, then does it mean that A must be A? So it seems trivial, but good that we should begin with proving the trivial things actually. Okay. Now trivial things can be proven by anyone. Okay. The next is that imagine X is R, so I'm becoming specific now. Previous things were specific. And A is the Borel sigma algebra of R. Okay? So A is the Borel sigma algebra of R. And you take a map f of x equal to x, for example. And a constant map at an identity map. Is it measurable? What would be the f inverse of A to plus infinity?
It would be e to plus infinity.
Itself. Okay?
A to infinity.
A to plus infinity itself. Now, is it Borel? So in other words, does it belong here? Right?
Yes, sir.
It does belong here. So in other words, this map is measurable. Okay. Are you getting the point?
Yes, sir.
What if, okay, here's the thing. Okay, that's not that. What if I replace this with a continuous function, any continuous function? Okay, this is continuous. What if I replace with the any continuous function? Good point to reflect upon. Alright, so enough of examples. Let's move on. Some characterization of measurability. Okay. So I would like to do proposition. Okay. If I have an abstract measure space XA, okay, and F is a real valued map, okay, map, not measurable necessarily. Then following are equivalent. Then following are equivalent. Number one. In other words, F is measurable if and only if one of the conditions is true. X in X such that F of X is bigger than A. Second, X in X such that F of X is less than or equal to A. X in X such that F of X is less less than A, strictly less than A. Okay. The fourth is x in x such that f of x is bigger than or equal to A. Okay. So in other words, it's not that the only this semi-infinite interval is because of that, you have the measurability, but you can use any of these conditions to prove that f is measurable. Okay? Is it making sense? Why this guy should follow from this? Oh, sorry. So my claim is basically that this belongs to A implies, this belongs to A implies, this belongs to A implies, and this belongs to A, and then return to this. That's what we would like to show. If this guy is an A, then this must be an A. And then everything should be an A. So why 1 implies 2 must be true? Trivial. How about 2 implies 3? Okay. Why this must be true?
Subset.
By the way, from 3 to 4 you can also say that the same thing. Okay?
Yes, sir.
Maybe. So the only interesting thing would be 2 to 3 and then 4 to 1, something like that. Okay?
यही प्राप्त करते हैं आपको
Mhm.
यही प्राप्त करते हैं आपको and you know sigma-algebra is monotonic class every sigma-algebra is monotonic class
Mhm.
so there are two possibilities of
Have we
monotonic class.
defined monotone class? We haven't yet. So we don't need at the moment. There isn't anything about monotonicity of the class I find that we need.
So third one is
So
interesting.
here are two identities.
Third
And
one is
try to think that using these identities, which follows from which angle. So I'm saying that the set that x, f of x bigger than or equal to A is same as the intersection of n equal to 1 to infinity x such that f of x is bigger than A minus 1 over n. Okay? That's one identity. And the other is that x, f of x bigger than A is equal to union of n equal to 1 to infinity x such that f of x is bigger than or equal to A plus 1 over n. Okay? So first verify these are true, okay, as a set, and then think about this identity helps you to follow what from what actually.
This is 4 to 1.
Think about it. How does they help you? So in other words, this is what you call the enough, to prove things out. Okay? So let's try to write a complete furnished proof of it. Is it making sense? Here is another interesting proposition. So what we are doing essentially is that okay, measurable functions and what are some key properties of it. These are some of the key properties that you always keep in mind. Okay? So now imagine X is not only a set but it's a metric space actually. So you have some way to measure distances in it. Okay? So X is a metric space. And let n go. And A, so X is a metric space, and A contains all open sets. Okay? A is a collection of all open sets. Okay? So that A is a topology of X essentially. So if A contains all open set, essentially it becomes a topological space. Then, and you take F from X, this topological metric space, into R that is continuous. Then what? F is measurable. Okay. Is it making sense? So what do you have? You have a metric space, and A is a collection of all open sets. It's essentially a topology, use topology on X actually, and then you take a continuous map on a metric space. Then every continuous map on a metric space is measurable. Okay. Why this would be the case? So you have to think. So how does a continuous map behave actually? What's the very basic definition of a continuous map between, say, for example, two topological spaces?
Open set, open set.
Very simple. Okay. What would be this set then? This is what? This is, by definition, F inverse of A to plus infinity. So what we can say about this guy? So only A plus infinity. So you see, on R you have this trivial topology. Okay? Euclidean topology. So that's an open set. And F is what? Continuous?
Continuous.
So F inverse is what?
Continuous.
Open is mapped onto open. So this guy belongs to it. And what this shows that all continuous maps on metric spaces are measurable. And what this shows? It shows that measurability is a weaker condition than continuity. So all continuous maps that you learn in your analysis, calculus, and so on and so forth between topological spaces, okay, or maybe metric spaces essentially, okay, are continuous maps. They're measurable maps. Okay. So in other words, if you are defining the integrals for measurable maps, continuous functions are there. Okay. You haven't lost continuous functions. So in other words, when you are doing this new theory of integration, okay, new theory of integration should be, compatible with our old theory of integration actually. Or we must be able to deduce that as a particular case of our set. Okay. Are you getting the point? Is it making sense? So what does follow from here? Think about it. Then, all such maps, F is a map from R into R. And it's continuous. So it's measurable. Okay? F is a scalar field, a map from R into R, which is smooth.
Why do
Measurable.
X to be metered spaces?
Uh-huh.
Why do we need X to be metered spaces?
Because we want these guys to be open. Think about it. If X is not a metric space, then how you can have this notion of open sets? And then how you can have this A as a collection of open sets?
Okay.
So what is the meaning of having open sets in an arbitrary set? We don't know. You need some topology to talk about
Yes.
open subset. Is it making sense? Okay, so if I have, we're doing in differential geometry, if f is a scalar field, measurable. So in other words, this really generalizes, so you can write lots of, particular mathematics